Hello, everyone. Welcome to today's episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, ask us questions during the episode and we get to them as well. So without further ado, I guess let's get started. So we've been doing this whole series on like different particles and their special roles that they play and wanted to delve into. We talked about like the inflaton, a few brief mentions of the photon, his Higgs mechanism, and then the graviton. So we've talked about these different things, but Tim, I remember we were discussing about like what particle would be considered like keeping particles in line, kind of like a nuclear warden, as we've titled this episode.
Yeah, I think the few particles that we've come across, that we've discussed so far, kind of has a certain flavor. And these, I think we would safely say most of the ones we talk about are what we call mediator forces. They're kind of, I don't know, how do you put this? It's kind of the arbiter of, there's almost like, I don't know, like the Star Wars vibes a little bit. Like they're
Mhm.
the keeper of orders to some extent. And amongst all the forces, I would say in my mind, one of them particularly stand out as having kind of a most interesting, I guess, kind of role in terms of the particles that we see in our universe, and that is the gluon. And I think we've had this discussion before this episode that exists. So I'm we can dig into that. What do you think, Mikey?
Keeping the peace. Yeah, I mean, yeah. Yeah.
Keeping the peace. What does that mean to keep the peace? Like it seems things
May,
seem pretty peaceful.
maybe a little bit of context is needed, right? Like when we talk about most of the forces in nature,
Hmm.
a lot of the forces kind of just, sometimes it's attractive, sometimes it's repulsive, right? If you think about gravity, like we're kind of on the surface of the Earth, but if we want to escape it, it's not. I mean, it might be somewhat difficult, but it's not impossible, right? We can go on a rocket and just blast off, like we'll be off the Earth, right?
Hmm.
Now that's gravity, and in the case of electromagnetism, chemical reaction is a way to escape that force, right? Electrons can be stuck in a hydrogen, but
Hmm.
you light up on a match, boom, those hydrogen turns to water. Basically, the electrons escape the atom, right?
Hmm.
But the nuclear force is a little bit different, right? You can't quite just light a match and kind of have a nuclear reaction. Like, it doesn't quite work like that. And in fact, the nuclei are kind of tightly stuck together, and you can already kind of feel like this is kind of unlike some of the other forces, and that is the undoing of the gluon. The gluon turns out it's particularly strong, and that's why we call it the strong force. It's particularly good at holding things together, so you can't just kind of like light a match and separate things. You can't just like blast things off apart, that at least not that easily. So the gluons is it's pretty convicted. It's pretty strong. It's like a warden is it's a good word. It's a strong character that kind of really keep things together. So
It is extremely unique, right? So, like, I mean, I think what Tim was alluding to is like, so if we think about every single force in the universe that we know about, they have this property where as you get farther away from them, their effect gets weaker. If you get closer to a magnet, the magnet becomes harder to keep them separate the closer you get them to, because the force pulling between the two magnets gets stronger as they get closer. And gravity is the same, which is why it's possible to actually escape the gravitational field. If gravity got stronger as you moved away, then it would be obviously possible to escape. It would be like a rubber band that just pulls you harder the more you pull on it. Um, and so, if all the forces we know about, none of them have this property, that the gluon has, where it's the only force in nature that gets stronger as you get further away from it. So what's the consequence of that? The consequence of that is that it takes more and more energy as they get farther apart. It takes more and more energy to try to pull them apart. And then I guess I'll just finish the story, but so what happens if you really try to pull two quarks apart that are bound by this, gluonic force? Eventually, you put so much energy into the system that you pop out quark-antiquark pairs, and I don't know. It's kind of a bad analogy, but sometimes I explain it like, it's like cutting a worm in half. Like you just get two worms instead of killing the worm. Yeah, it's a very limited analogy, but it leads to this very weird phenomenon, which physicists refer to as confinement, where you never see a quark by itself, because it always, there's this mechanism that guarantees that it's always bound with at least one other quark.
Wait, so okay, hold on. Few things I want to take a step back on. Number one is like, can we give a high level overview of like what are quarks and like what are like gluons in some sense? Like we talked about strong force, but I think maybe some more context on like what is kind of the significance of that, and then also if the strong force gets stronger as you go further away, why don't I interact with it like directly as I am right now?
Yeah,
Can I do the first one? Can I do the second one?
yeah, sure, go ahead.
Okay, what was the first one? The first one was
What are quarks?
Like quarks,
Yeah.
quarks and
Oh, yeah.
gluons and stuff
So
like
I
that.
think for the purposes of discussion, we can think about it in the following way. Like, if we have like a positive and a negative magnet, they're going to attract each other through the electromagnetic force, right? Everybody knows that from whatever, like high school physics or whatever. And so if you take this to the particle level, you can have a particle called like an electron, and then its antiparticle called the positron. And those two particles are attracted to each other by the electromagnetic force, as they teach in probably college physics or something. Not probably high school physics, right? Also. And so there's another force of nature, fundamental force of nature, which we call the strong force. And that there are these particles called quarks and antiquarks that are basically attracted to each other by this strong force. And if you look inside the protons that make up the center of every single atom, you would see that each proton is made up of 3 quarks that are kind of stuck to each other by this strong nuclear force that we were talking about. Go, Tim.
Yeah, let me add a little bit on that. It's a little bit more complicated than that, and that's one of the reasons why it's not so intuitive, right? When we learn about in physics, we learn that the opposite charges attract, and same charges repel, right? That's the simple rule you learn in electromagnetism. It's somewhat analogous to like magnets. I mean, if you're not familiar with charges, like if you stick the magnet with the same pole, you feel this repulsion, and if you stick with the opposite pole, they will like to stick together. But for this strong force, it turns out there are like there are 6 possibility. I think it's 6, right? There's like instead of just having one type of charge, there are 3 types of charges, and that's why we call them color, analogous to red, green, blue, even though it has nothing to do with color whatsoever. This is just a nomenclature, right? So you can have red color and like the anti-red, blue anti-blue, and then green anti-green, right? But it's not as simple as like, oh, the same charges attract, different charges repel. Like you can have many different combos. Like what happens when an anti-red sees like a blue, or like a green sees an anti-blue, something like that. You get all these combos. But the complication is that color themselves, when they interact, they can exchange, emit and absorb gluons, but the gluons themselves attract one another. Now that's the kicker. There's these self interactions, and ultimately, when you add them up, all these charges, all these complicated things together, the forces can get quite strong. Like the summation of all that becomes like a really kind of unintuitive kind of forces.
You describe it as like compound interest. Maybe not.
Yeah, I don't know. It's almost like it also is it almost like you have like six different bank accounts that you can wire from one to another. I don't even know how that works. Like it must be some kind of like it almost sounds fraudulent. Just like these, if you think of these as money, it's like many different types of currency going back and forth. It sounds like a serious money laundering business, but
Gotcha, gotcha. I mean, so do we see this with electromagnetism with like a photon?
we
And if
Photons
don't.
don't
if
interact with other photons.
There, yeah.
That's why the strong. It's like a. What's a good analogy for it? Like,
I actually a good analogy is gravity a little bit because gravity is the forces with energy. So graviton themselves technically can also emit other gravitons. And when you add all that mess together, when gravity becomes really strong, you get a black hole.
Mhm.
Like that's how intense it is. So kind of imagine that all that mess of gluon, just gluon strong forces mess, when you add them up together, you get some like kind of like a crazy soup. And I don't want to say it's kind of like a black hole, but a little bit, like sort of. It's just like a muck, like a black muck.
wait,
We
are you
call
talking about this like ADS QCD thing that people used to think about?
Yeah, there physically actually this analogy is not terrible. Like there is reason to believe there is similarities. So, I'll just throw it out there for our
uh
listeners.
That's
so
actually an interesting part of the story that I totally forgot about.
yeah, so what you're saying is that gluons can interact with themselves, these force mediators of the strong force, and that gives rise to this very like soupy, like chaotic mess inside of like protons, neutrons, these various particles that contain quarks. Is that fair?
Yeah, I think that's fair, and I feel like the analogy might even apply. Like the black hole analogy might even apply. It's kind of like the proton. Like imagine all that interactions stuck in a
Mhm.
proton, and the fact that the quarks are kind of cannot escape out. I think it's a little bit similar to like you can't escape out a black hole. Not exactly the same, but there's some
Hmm.
analogy there, right?
Hmm.
Um, like in order for a quark to escape, you have to put in a lot of energy to kind of extract it out, right?
Hmm.
Like it's not obvious. Um, and that leads to the next question, right? Like, is it why does the energy increase as the distance increase?
Yeah, like why does it get stronger as it goes further away? And like, why am I not seeing that now? Like, why am I not bound to like, someplace? I don't know.
Yeah, I would say
Wait, hold on. Since you talked about the black hole thing, should we just talk about like the string picture behind all this? Because it kind of goes back to what we were talking about before. Like if you have a quark and an anti-quark, you try to pull them apart. There's all these gluons being exchanged between them, and the force gets stronger in some sense because these gluons are interacting with each other. So the force is essentially building up. The more gluons you have, the more self interactions you can have. Um, and this actually starts to form kind of a string-like object. And the force actually, or the potential actually grows linearly as you separate them, which is exactly what you'd expect from like a string-like object. And in
Mhm.
the picture that Tim was talking about, where you can think about these things in kind of a black hole language, those strings actually correspond to the strings in string theory. So you can actually view this kind of system as either like a pair of strings or as
Hmm.
like two individual particles bound by some strong force.
Whoa,
Yeah.
that is interesting. Yeah. Well, okay. So I guess like would it be like analogous to think of it as like a rubber band that the more I stretch it, the more force is exerted to like pull them together, as you were saying
Absolutely,
before.
yeah. Yeah,
Yeah.
it's like
Okay.
absolutely rubber band.
Yeah, well,
Uh,
I would say it's a little stretchier than a rubber band because rubber band can
mm,
kind of snap, but these are like
mm,
way harder to snap.
Infinitely stretchy rubber band.
Yeah, like super duper stretchy. Yeah, I mean,
I
you,
see.
you can think of like a good rule of thumb is that nature tries to kind of tends to try to minimize the energy of the system in some ways, at least
Hmm.
given the constraint of the problem, right? given that gi- gi- given that there are these like different colors for quarks, right? And you
Mhm.
know that whenever the analogy in electromagnetism is that whenever you have charges, positive or negative charges, there's a possibility for them to attract, right? So whenever something has a net color, like something that looks reddish, right, then it
Mhm.
has the possibility to attract other stuff, right? So if you then do this comparison, that means imagine you have an object that has net color charge red, right? Then it has then it then and because the forces increase, I guess it doesn't increase. The energy increases the further away you're from an object. This
Mhm.
object will have infinite energy because you can have something that's like 20 light years away, and that will have
Mhm.
so much energy attracted to this red colored object, right? So
Mhm.
nature doesn't like that. Basically nature
Mhm.
says whenever you have anything that has color, in the strong force sense, I'm gonna
Mhm.
try to eliminate it. Like we do not like that. So nature try to find a way to get rid of that color. The way they do it, there are two ways. Either you smack like some anti-red, even though that I guess there's no analogy. You can't just have anti-red color, but you mix them up. So from far away, the color becomes neutral, gray, right? Then this infinite energy paradox almost will not happen. Or you can kind of mix red, green, blue together all together. Then you get like white color. Also, it's kind of color neutral, right? So that's why and that's the reason why we don't see this effect in real life because nature because if the energy increases, the more distance you have, nature will try to forbid that from happening. So every time you have objects that has color, like a quark or a gluon, nature will try to wrap other particles around it to kind of corral it around such that it will the whole object on average will have no color whatsoever, so that the whole system becomes confined, almost like in a jail. Basically, everyone will be like stuffed in a jail and just like do their own thing, basically.
I guess one thing I wanted to clarify for the audience is like the use of the word color, because like it almost seems like these quarks and gluons like are actually like, like someone took a paintbrush and like colored it red or like green or blue. When you talk about colors, like you're not actually talking about like actual red, green, and blue, just more as labels. Is that correct?
Yeah, these are absolutely labels, analogies. They're imperfect analogies. I wouldn't take them too literally, but it's really
Hmm.
hard to talk about three types of charges in our ordinary daily lives. It's just hard to wrap your head
Hmm.
around. So color, I think, gives you a way to visualize it, I guess, a little bit, but they're not little colors.
Feels pretty quickly though, because there's no such thing as anti-red.
Yeah, like you can't have anti-red. What's anti-red? Like yellow? I don't even know. What is
You
anti-red?
have to look at the primary color wheel. So actually, I wanted to ask a question to give the audience a bit more intuition. If photons had the same property as gluons, how would electromagnetism change? Like, what would that mean? Like between repulsion and
Oh,
attraction?
that would be nasty, I
It
think.
wouldn't be no. What you mean if the electromagnetic field confined, like, or
We wouldn't.
If it's self-interacted, I don't know what that means. I guess like it might be confusing to the audience. What does it mean to self-interact? Why is that significant?
Then we wouldn't see light. I think light wouldn't be able to move freely because it will always be attracted to other. It will get distracted a
it wouldn't
lot.
be light. It wouldn't be. It would just be another strong force.
Yeah, yeah. Basically, you wouldn't see it. Like if you turn on the light bulb, the light's trying to come at you.
Oh
Mhm.
yeah.
All
Okay.
of a sudden, it try to interact with everything else around. It would never reach you. It would just be like stuck, basically.
Yeah. Everything that was positively charged, everything that was negatively charged, would just like uh instantly find their closest partner and just pair up until everything was electrically neutral. So you wouldn't have anything that's electrically neutral in the universe. Like, my body is overall kind of electrically neutral, which is why if you put me in front of a magnet, I'm not going to fly towards it. Um,
Yeah.
and yeah, but you can make things that are not electrically neutral, like the magnet itself. But
No, you
it,
mean charge. You mean charge. There's nothing. Yeah, you wouldn't see naked charge.
sorry.
You said there wouldn't be anything neutral. You meant there wouldn't be anything charged. Sorry.
Oh yeah, there wouldn't be anything charged. Yeah, sorry, I got it backwards.
Mhm.
Yeah, because because everything would just find their nearest partner and partner up, and I guess get confined in these jails, as we are analogizing.
What would happen with the opposite case, like repulsion? Like, say you exist in a universe where there were only like charges and photons self-interacted. Would the repulsion be like exponential? Like, what would that be like?
You only have it's actually hard to have only like charges in a universe, so that's kind of hypothetical.
Wait, you mean we remove the gluon? I mean, that would be kind of terrible, right? Because we wouldn't have nuclei anymore. We just have quarks.
So
No,
I
I mean,
didn't
like
mean
having a
gluon.
particle species that only has a positive charge, that might be impossible, Tim. Is it? Like there might be fundamental restrictions against that.
So I'm trying to just give the audience more of like intuition about like what does it mean to self-interact from a repulsion case rather than just attracting. Like if you put two protons, or not protons, but say two fundamental positively charged particles of +1 charge next to each other with photons that self-interact, would the repulsion be like extreme, or would it be like no repulsion? Or would there actually be like a attraction?
Tim, can asymptotically free forces be repulsive?
That is. Let me think.
I feel like the answer is no.
I feel like the answer is no too. It tend to be repulsive. At least from the analogy from gravity. I hesitate to say
Well,
this.
the reason why gravity can be repulsive is not really aligned with the reason why electromagnetism can be repulsive.
Well, gravity cannot be repulsive. That's unless such strange things
like
happen.
dark energy.
Oh, sure. That's something different.
That's like a whole separate thing, though.
Yeah, that's a whole separate thing.
Yeah.
I hesitate.
The electromagnetic field is special because it can be repulsive.
Yeah, I mean, look,
Yeah.
look. I mean, I don't think these more complicated forces is necessarily strictly attractive or repulsive. I think you could cook up color charges to the extent that to make it repulsive, right?
But then that would be an effective theory, right? It wouldn't be actual theory. The actual gluon can't be repulsive, right?
Well, I mean, you could set up. I'm sure if you fix a particular charge, like a blue or like anti-green, I don't know what combination. Some of them will be repulsive, right? But because the color can change. But if you just follow a system and as time goes on, yada yada, things happen. Like
it's kind of like a wash, so it's hard to say if it's how much attractiveness is in there, how much repulsiveness is in there, but
yeah, like you could set up a situation in which particles definitively repel each other, but that's not. Yeah, I feel like that's not the best. I mean, that's a contrived scenario. Like in real life,
like it's really hard to name quarks because their mediator particle is so strong and quarks are so light. A lot of them, it's so easy to pop quarks in and out. Like if you even try to separate them a little bit, then two new quarks pop out, and then the other two quarks, things can happen, and you can annihilate quarks. It's really hard to keep track of quarks.
Yeah, I guess I want to add that.
Very quirky.
Yeah, I guess I want to add that like the reason we struggle so much to answer simple questions like, oh, is it repulsive, is it attractive? Because in particle physics, the way we think about forces are a little bit more nuanced. Like forces just cause a lot of interactions. Like things can
cause change. It's something that causes change.
Yeah. Like saying something that's repulsive or attractive, it's kind of like a really superficial look, right? Like a force can break things up. It can fuse things together. It can cause excitation. It can de-excite something, and different forces can cause different ratios of all these things happening together. It's hard to really just say, hey, is it attractive, repulsive? I think.
That's fair. I can accept the nuance of that. So I want to come back to two questions. One was one that I asked before, was about like why don't we see the strong force at larger scales, like the scale that I observe? Why do I mostly see electromagnetism and gravity. And then the other thing is like we mentioned quark confinement several times. So maybe describe to the audience like what that is and like why you can't do it. Like why is that so hard? Why have you not seen a quark by itself?
I think that's
So
the
let's
same
start.
question. Those two questions are the same.
Yeah, it can be. I didn't want to assume that,
I mean,
but now that you, yeah.
maybe I'll give a little bit of historical context, right? Like when this phenomenon was discovered, this is called asymptotic freedom or confinement or many different names. Uh, People were surprised. They thought it was like a mathematical error. They were like, this can't be possible. They computed some of these function and that says, hey, like the energy increases as distance increases. That's so non-intuitive, right? Like everything we've studied
Mhm.
so far is like the farther away you're from something, there should be less interaction, there should be less energy. So by no means is this thing intuitive. But like after a while, people think about it for a long time. They realize that like like this behavior exists, and this is why this is what Nobel Prize 2008, I think. I
Mhm.
forgot. I think is it David Gross, Frank Wilczek. There's another person. Glass Glasslow, I think. I could be wrong with the credit, but of course many other physicists working on it. Um,
Mhm.
but but through like this kind of physics is actually very hard. Um, because these are all fully quantum mechanical particle physics behavior. Like the math is very difficult. Like it's not just like F equals ma or like E equals mc squared. It's not just one equation to describe it all. It's like many different
Mhm.
equations that you can't really solve, numerical simulations, right? But then the results that the energy actually increase with distance, Mikey, correct me if I'm wrong. I don't think those results literally come out of hand calculation. Those are mostly confirmed by numerical evaluations, like what they call
Wait,
lat.
no, doesn't just the asymptotic freedom imply that?
No,
Like
I
that the
think
coupling constant increases with
that tells you that it may be true, but in some of the regimes, the calculation are not so reliable. So I think they have to like to really
Oh yeah,
confirm
yeah,
it.
yeah,
Yeah.
yeah. That's true. Yeah, because you can you by definition you can't trust the calculation in those places, but
Yeah. So I think to really
yeah.
confirm it, ultimately you have to run a really complex numerical simulations. These are called lattice
Mhm.
calculations that show you that hey, energy does increase as you increase distance, and then you go back to do some calculation using strings, quantum
Mhm.
mechanical strings, and you show that hey, this is this is this is similar to a behavior that for a string behavior that will also expect that, but otherwise. And then of course, and then we physicists come up with some intuitive explanation that we believe is happening, but those aren't. I feel like those are not perfectly rigorous, but I don't know.
Mm.
Maybe,
No description is perfectly rigorous, right?
yeah. So I don't know if I give you a good enough answer. Like this is yeah, the best we can give, the best answer we can give you is probably the string picture, I would say. Yeah.
So I'm still trying to understand this. So we like you guys talked about asymptotic freedom. Does that mean like at like some large actually yeah, what does asymptotic
Oh
freedom
yeah,
even
sorry,
mean?
yeah. I mean, yeah. So what asymptotic freedom means, it's a technical term that people talk about to describe this phenomenon. And yeah, we talked about without describing what it is, trying to gloss over it. But like technically what it means is the fact that okay, so if the force gets stronger when you try to pull two quarks away from each other, then if two quarks are right next to each other, there should be almost zero force pulling on them, right?
Yeah.
And in that case, the closer they get to each other, the more they're essentially just like feel no force at all. So
Hmm.
if you imagine you put them like even infinitesimally close to
Yeah.
them or asymptotically close to them, then
Hmm.
they essentially behave like completely free particles.
Yeah. Yeah.
Mm.
So I guess it's
Oh,
kind of
so
like
that's asymptotic freedom
yeah,
Yeah,
is like you put them asymptotically close to each other and they're effective like free
yeah,
particles, no
that's what the
interaction.
theory exactly
yeah,
says. Yeah.
yeah.
Oh,
So
Very, very
okay.
weird.
it,
Very, very weird.
it's really it's also almost like a paradox. Like by jailing these quarks into a closed, confined, small confined space, they actually feel more free. They actually feel
Actually
better
set
about
them free.
themselves. So
I don't want to be cynical and make any analogies to human thought processes, but I'm kidding. I'm kidding. So okay, so that answers that question. Now, Mikey, you mentioned that like quark confinement is like the same question or related. How is that related?
Oh, sorry,
Tell me.
related to
Related to
what?
like why don't I feel like the strong force at larger distances?
Oh,
If it's so
because the
so
effects of the
damn
force,
strong,
yeah.
yeah.
I would say because of the fact that when we say confinement, we mean like essentially we do mean the effects of the force are confined, like locked away in this small size that you can't see them when you zoom out.
Mm.
And the reason why that happens is because a combination of just two facts: the fact that the gluon, the strong force interactions get stronger as you try to pull quarks apart, and then quarks are not that heavy, or most of them are not that heavy. So it means that if you try to pull two quarks apart, you're going to build up enough energy in the string to pull a quark and an anti-quark, out of thin air, and then you just
Mhm.
get like these two quark anti-quark pairs, which we call mesons,
Yeah.
which is just a name for quark anti-quark pairs. But so it's weird. It is weird. It's like the balance of these two things guarantees that you'll never see the effects of this force unless you look down a certain distance scale.
Yeah.
And it's not like it had to be this way, right? If quarks were really, really heavy, then they would essentially act exactly like rubber bands. And we actually call these hypothetical particles quarks, which is actually the namesake of this podcast.
Oh, like heavier quarks as quirks?
Yeah, so if you imagine that maybe there's another force like the strong force,
Uh-huh.
but it's completely disconnected from our universe, and maybe in this like weird version of quarks, you have like all the quarks are really heavy. Then it's not easy to pull them out of thin air. You have to put so much energy into them, and so then they just kind of like do this kind of stretchy, stringy dance that Tim can tell you a lot about, much more than me.
Yeah. So let me see if I can give an analogy to understand this in like an everyday experience. So it's like if I have like two, let's say really like I don't know, like something like really light, two really light objects attached to like this rubber band, and I pull it in just enough where the rubber band snaps. It's as if that energy of it snapping allows it to create like two new rubber bands, but having like another light thing attached to the end of it. And so
Exactly.
you don't
Yeah.
Yes.
see it. Okay. So it's kind of like the energy I have to put in to actually break it apart is what creates new things. So it's actually never broken apart, but just,
Yeah.
yeah. Okay.
Oh, it's literally like nature is trying to hide this from us.
Yeah.
Like it just kind of orchestrated this overly complicated scenario just to make sure that you never find out this force exists.
Yeah.
Oh, wow.
I mean, it's kind of like a weird analogy. It's almost like a buddy system that the quarks keep each other in check. And I hate to use like the criminal justice system as an analogy. It's almost like we just shielded away from the effects because
Mhm.
they kind of just jailed away, so we don't see it. But
I mean,
Mm.
that is a good analogy with the criminal justice system, right? Like that's there's not enough press given to the private prison industry, whatever.
So gluons are like the CEOs of the private prison industry is what we're going for, Tim.
I would say
Just keeping.
they're more deep in the muck because they are personally responsible for holding the hands of like these quarks and matching them together. Like they are really the ones who are like physically wrangling them to each other because those strings between them like the tie
Mhm.
what we describing those strings
Uh,
we literally call them what like um, some kind of flux tube. They are literally made of gluons, right? Like they gluon flux tubes, basically. They are the
Mhm.
gluon themselves. The gluons themselves are the stranglers, or the what do you call the zip ties or whatever you call it.
Mhm. Got it. Got it. So I realize we're like almost at time. I want to give you guys some time to like any concluding thoughts before we head out.
Yeah, I can go first. Yeah, I think like I guess we've been going through like the different kinds of particles, and like in the past, a lot of them are kind of like hypothetical particles. But I don't know. I think this discussion has been nice for me because it really has kind of reminded me of how special this universe is. Like the fact that we have something like the strong force in our universe, and it has exactly the kind of properties that we have. This allowed it to have rules where like three quarks combined together make something with exactly a +1 charge, which we call the proton, that exactly balances this seemingly unrelated particle that happens to have exactly -1 charge, and create this perfect balance called the hydrogen atom. Like it's just it's a weird thing that such a thing exists in our universe and is crucial to our survival. And I don't know. I guess a whole episode dedicated to highlighting the idiosyncrasies of this odd phenomenon, and yeah, it's very well worth it.
And I would like to say that even though today's episode we're focusing on some of the differences on how the gluons behave differently from like particles of light, or there's some similarities between gravitons and also differences. Let me just remind the listeners that even though their properties are drastically different, what's remarkable is that the mathematics behind them are almost identical. Like the difference between gluons and particles of light is just the number between 1 versus 3. If you just say, hey, like what if I increase the number of light particles from 1 to, well, not necessarily 3, it tends to be 8 in this case, and make sure some certain mathematical, we're not going to go into details on that, and make sure
squared -1.
Right, yeah, 3 squared minus 1, let's say. Let's not go into details on that, but let's say if we extend the mathematical machinery to make it consistent, it turns out that is the behavior that we get. And it's remarkable that the same mathematical paradigm is able to explain these forces. Like nature takes full advantage of these diversity of outcomes based on the same mathematical principle. And that is something, and this is the reason why we believe so strongly that our standard models of particle physics works. I mean, it's completely remarkable. Like no one would have guessed. Like if you tell someone, I don't know, 50 years ago, but like that was just crazy, right? Like how could that possibly happen? But here we are. Like it works. So.
Okay, 50 years ago, people might have believed it could happen. Like, I think you're thinking it's the year 2000 right now.
Oh, that's true. Yeah. Maybe 70 years? Is it 80?
60, 70 years ago would be, yeah. Maybe.
Yeah. So we have come a long way. So.
Yeah, that's really interesting that you can take the similar mathematical structure as photons and just make 8 of them with slightly different properties, and then it would work.
Yeah.
You get everything for free. Yeah, everything we talked about.
I would say almost the same equation, but drastically different consequences. It's almost
in fact,
like
it's in Tim's background right now.
It's one of these
yeah.
equations. Yeah. But anyway, we won't go into details.
Yeah. All right then. Well, on that note, I want to thank everybody for joining us. And Tim, you mentioned you're not going to be here next week, right?
Yes. So
Okay.
we'll see you guys 2 weeks from now.
Yes. I feel like we should let the audience know whether we're doing it the following week rather than saying we do it every Tuesday.
We try our best to accommodate.
Yeah. Yes. Yeah. So we'll see y'all 2 weeks
These
from
are
now.
weird months.
All right.
Yes.
Yeah. Bye, everyone.
Okay. Bye.
Bye.
Restart.